Okay, all right, good. So we start the recording for the lecture today. Uh, the the topic we are going to talk about is linear regression and multiple regression. I believe that you or most of our students have been exposed to this topic one way or another, more or less, and it's a very important topic. So, uh, and because it's very with a lot of reputation in the real world scenario. It studied the relationship between the two variables. What is different from all the previous section is that from this section and on, we start to talk about more than one variable. Almost all the chapters we previously discussed were about the univariate data. Now, in this section, in this module, we want to redirect our focus to bivariate and then multivariate data. Bivariate data means we have two variables observed from one subject, from one experimental unit, and so forth each time. Then you collect two related variables at the same time. Okay, and then therefore we are interested in studying the relationship. Then to describe that kind of relationship with the line, and then later more complicated, more advanced method will have to do with curve, like a nonlinear regression. Fitting sometimes the relationship is presented as a nonlinear relationship, so simple linear regression is not enough. But this is a foundation, so we start from here, and then we then study the rationale behind this simple linear regression. And then on the one hand, we describe the data, but on the other hand, we are more interested in using it as a prediction model to predict the behaviors of the bivariate variables. So this is the main goal for conducting linear regression. Then also we talked about multiple regression. This section is not the content in this chapter doesn't cover too much about multiple regression, but I included. And on the one hand, it's important. It's called because it's closer to the real world scenario. In the real world case, we most often in time we see things like this, like for example, the income. You know, if I ask a person and how much income he make per year, then I spontaneously I will believe I will relate that high level income or low level income to his education. Then also his or her age, and then his or her gender. Usually, male may make more than female. In this sense, in a way that's true. And then so what else? You know, at least these factors affect the income, right? And so it now becomes a scenario in which more than one independent variable affecting the unique dependent variable. So in this case, we call it multiple regression. Multiple regression. Okay, and so and of course down the road, if we got a chance, we may explore logistic regression. The differences between linear regression and logistic regression, or multiple regression versus multiple logistic regression, is that in logistic regression, the dependent variable is categorical, or you can say binary outcome. Okay, binary outcome, or binary is equivalent to binomial. And then if we relax a little bit, it may be multinomial. Multinomial. For example, use the same example I just mentioned. In case in case such a person want to make a loan from a bank, and the bank will either give you the full amount you apply to buy a house, or they will reject you, deny your request. Okay, so in that case, the dependent variable is approval or disapproval. In that case, is a binomial outcome, and that binomial outcome is a factor is dependent on the multiple independent variables. So in that case, it's a multiple logistic regression. And of course, if there's only one independent variable, then that's logistic regression. Simple linear logistic regression. So and so in general, the linear regression is a special case. Simple linear regression is a special case of multiple regression, and simple linear logistic regression is the special case of multiple logistic regression. Okay, and so we did this big picture in view. We now zoom in on the simple linear regression, and if we understand the simple linear regression, automatically you understand the rationale for multiple regression. So this is the approach that we use in giving this lecture. Okay, so the emphasis will also not be so much on the equation formula, because on the one hand it's try cumbersome to calculate it. On the other hand, you don't have so because of that, we usually don't have that much time to do that manually. And so since that's the case, we need to be more practical and let the computer do the work, but we need to know how to explain, make sense of the output from the software. Okay, so all right, so good. Now let's jump directly to the model. Here we can see it mentioned a multiple linear regression model. Okay, and there you can see one independent variable, one dependent variable, and there are k independent variable in the model, right? And if there is a kind of relationship, then the line will look like A. Otherwise, quadratic is nonlinear relationship will be like B or no relationship. Okay, and and in a sense, since this is only a simple linear regression graph, if you have two, that's extended to two independent variable case. In that case, you may consider this as x2 and this is as x1. So this axis as x1 and this axis as x2, and you have points all over in a three-dimensional as a cube instead of a surface, then whenever x and y moves together, y goes up or down in that cube, in that three-dimensional space. Okay, so this is a little bit idea. And then of course, if you have more than two independent variable, then it's hard to display graphically. But so you can just exercise your imagination. And rationale wise is the same. Okay, so if we reduce this multiple regression case to one independent variable, then it's a simple linear regression. All right. And our goal is to build a model where we can estimate y, and so we put a y hat to y, and then instead of B0, B1, we can only find an estimate of B0, B1. Okay. Well, okay. Let's get back to this model. Here we have a model, and every time this is a real simple linear regression model, because because for you plug in an x, you get an y, but that y is not actual y. You have to add an error term, error component, then you get the actual y. So this is you can model the data with this, but the problem becomes finding the beta 0 and beta 1. So we need to estimate the beta 0 and beta 1. Okay. And then we can use, sometimes we can use the normal distribution to model that to be in the model. Okay, now the rationale behind this is the least square method. This square method is like this. Okay, this is a relationship by x and y is negative. As x increase, y decrease, so it's negative. And now there's a point here, y actual value of y, but given an x here, is value of y based on the line is this much, but the actual value of y is this much. So the difference is this black vertical line, and we use EI to denote it. So for x1 is E1, x2 is E2, x3 is E3, E4, and so forth. And E is positive or negative depend on whether it's if this is actual value is below, then what the error is positive. And let me see. Oh, it's negative because the y1 is here and minus y1 hat. Y1 hat is bigger, so this is negative, positive, and so forth. So given that, and then we show, because if you sum up all the errors, then you get 0. And so because it's positive, negative, it will cancel out. So the way we do is similar to the calculating the standard deviation or variance by taking the square of to get rid of the negative. So the positive and negative term won't cancel out on each other. Okay. All right. So let's see. All right. So we denote it with sum of square of error. SSE is sum of squares of error. SSE. Okay. And so the end of this square line is the line that minimize SSE. Yeah, it's just so simple. any line, there can be many lines to predict the relationship, but there is only one line that will minimize the sum of the least squares. Okay, and that is that's the least square least sum of squares criteria we use in creating that simple linear regression model. Okay, later for multiple regression also follow the same rationale. Okay, so the way to do it is by taking the partial differentiation with respect to B0 and B1, because SSE is a function of B0, beta 0 and beta 1. So you take the partial differentiation, and in calculus, the way to get the maximized value is by taking partial differentiation with respect to the variable it has. Okay, so you set them to 0, then solve the system of equation. You will be able to find a beta 0, beta 1, which minimize the line. Okay, I won't get into the derivation of the equation because that is not necessary. Okay, let me make it bigger. Too big. Okay, so you can see that this is how it this is system of equation of 8.3 and 4, and it's also a simultaneous equation. And then system of equation, you will be able to get beta 0, beta 1. Okay, and then this is how you can get beta 1. Okay, and all the formula, but including the R, use this formula to calculate beta 0 and beta 1. Okay, so if you are given a set of data, then all you need to do is just to calculate these quantities, and then you will be able to get the sum of squares of, and then to get the sum of squares, and then the regression line. Okay. So that's it. Excuse me, ACE 8.2 section. Now, quality of the regression line, of course, if we use our intuition, then we may know that the smaller the error, the better. But there are different situations when the error term should fluctuate around zero. But if the error displays certain kind of pattern, then that means our model doesn't do a good job. Okay, it doesn't remove the pattern. Okay, so it's not a good fit. Okay, so this section is regarding how to diagnose the goodness of fit. Okay, let me see. Of course, let me see. Let me see. Okay, this section. Yeah, 8-point properties. This is properties about the parameters. We will skip this section. Yeah. 8.3. So and now that we see the goodness of fit for the whole model, we may also wonder if we want to make inferences on the least square estimators. because once we obtain the slope beta 1 and the intercept beta 0, we are in a position to use the theorem A21 to make inferences regarding these model parameters. Okay, and using these parameter properties to inferences means we can make hypothesis tests or create confidence intervals. Okay, we want to know how how what's the range? Okay, what's the range for that these coefficients beta 0 and beta 1? Okay, so this is then we use a T distribution. T distribution. Let me see. T distribution with n-2 degree of freedom to test for what beta 0. Okay. First of all, the mean sum square what has MSE. It can be shown that SSE always an independent beta 1 has a chi-square distribution with an n-2 degree of freedom. So MSE is defined by that. Okay. Now then, let me see. Okay, that's better. Look at this better. Procedures for obtaining confidence intervals for beta 0 and beta 1, because we talked about making inferences about beta 0 and the beta 1. Okay, so you first use the data to calculate this, and then use a formula to compute beta 0 and beta 1. Okay, which is here. We saw it previously. And then we compute SSE, sum of square error. And once we have SSE, we can calculate some MSE, because MSE is mean sum of square error. Means sum of square error. Okay. And N is the number of pairs of observations, but we have 2 parameters, so we minus 2, n-2 to get a degree of freedom, n-2. So with this, and we can, based on the formula here previously, okay, T distribution, based on T distribution, you know, let's use critical pivotal method. If we use pivotal method, okay, that the probability of T beta 1 less than or greater than the probability that is enclosed by this value and negative this value is what? 1 minus alpha. Okay. If you recall how we calculate the confidence intervals, you will see that the T less than or equal to T alpha over 2 n minus 2 as an upper bound, and then T alpha over 2 comma n minus 2 as a lower bound. So, and the probability of that happened is 1 minus alpha. And then you plug this in here, you plug this in there, and then so this is less than or equal to T alpha over 2 n minus 2 and greater than or equal to T negative T alpha over 2 n minus 2 on both sides. Then you multiply this on all sides and then rearrange it. You will be able to isolate the beta 1 in the center, in the middle, in the center, and then to be enclosed by the upper bound and lower bound. Thus, you construct the confidence interval. Okay. Okay, and same way for beta 0. Okay, so you don't have to memorize the formula, Excel, R or other softwares will usually calculate this for you. Okay. All right. Yeah, you can refer to this example yourself. The rationale behind the formula are this. Let's just look at the result, of which we obtain a 95 count interval for beta 1. Okay, because we don't really know what beta 1 is. We can only estimate. And so with linear regression 9, we are able to find a beta 1 estimate for it, but that's only a point estimator. So there's only a point estimator, then we need to construct an interval to make inferences about it. Okay. All right. And also, if you do hypothesis testing, then you do it in a similar way using the same test statistic. Okay. Again, you don't really have to do this manually, but if you need to, you know how to do it. Yeah. Okay, let me see. Now it's almost 30 minutes. Okay, let's skip to predicting a particular value of y. So given you regression 9, given the regression 9, now, and you also have estimated for the beta 1, beta 0. Now, can you predict the y? Okay. We mentioned that describing is not the main goal. The goal is that we may be predicting a particular value of y for giving x. Okay, and that is so this is our goal. All right. And so this is a scenario, the step-by-step to the way to calculate it. Okay, first of all, you find the difference of an estimate. The particular value of y, actual value is y, but you estimate it from the formula is y hat 0. Okay, given x0, then your estimate is y at 0, which is a mean average. Okay, and then so the difference is like that, but then you take the expected value and it should become the 0. That's the best estimator. Okay, and so you develop it all the way, take the variance of it and so forth, then you can approximate that that error to follow the normal distribution with this as a variance term. And now you standardize it, so forth, you will be able to get the construct a confidence interval for y, and that's the formula. Okay, so we see how to construct a confidence interval for beta 0, beta 1, and how to construct a confidence intervals for the given, for the estimated, the predicted y value given the x value. Okay. Yeah, you can refer to this yourself later. And correlation analysis. So given an x, we can find the expected value of y. Then x and y are correlated in a sense according to this measure of r. Okay. So this is how you calculate r. Again, upon looking at a complicated formula, you don't want to, and I don't expect you to calculate it. So you just use a formula and then follow it. Usually, R will give you that number, and then you use that number to say something. Okay. Normally, when R is close to 1, it's positively strong. It's close to -1, it's negatively strong. If close to 0, and it's weak. Okay, if it's 0, then there's no correlation. Okay, usually 0.6 or 7, positive, negative 0.6 or 7 are a stronger relationship. Okay. Then for linear regression, this is yeah, this is just a metric. Okay, how you use a metric to calculate it, and use a metric notation to stand for to calculate the beta 0, beta 1, and so forth. And so when you have multiple regressions, this is the rationale behind it. Okay, so here you can see if you were given a multiple x, and let me see. Oh, this is not a multiple. This is yeah, because you only have beta 0 and beta 1. But if you have multiple regression, then this is like here, and you know how to do it with the metric. So this is the rationale that you see. Now one independent variable, one dependent variable, y has two independent variables, and so forth. Okay, now here's a multiple regression for ANOVA for multiple regression. First, we want to see if all the coefficients are 0 or not. Okay, then you use R is LM. Okay, the function for conducting a multiple regression in R is LM. No. Yeah, and then you can get this ANOVA table, and based on that ANOVA table, you will be able to, and then you look at the F ratio, and there are also p-value associated with it. If the p-value is very small, then you will be able to conclude that at least one of variable are not equal to 0. Okay, this is the multiple regression. The way we do multiple regression. For example, this example, you have two independent variables, and now this is the ANOVA table, and p-value is here. P-value is not too big to say no to H0, so we cannot reject null hypothesis at 0.05 value. That means we cannot exclude the possibility that beta 1, beta 2 are 0. Okay, and so forth. Okay, well, I think it's good to wrap up my lecture for today. Almost here. Now, I didn't assign too many questions for this assignment, and there's no manual calculation in the real sense. But according to this semester, I add more R for you to get hands-on experience. So you can refer to the end of the textbook where you have R code. But I don't necessarily use the R code for the question. Actually, in fact, I use in fact I quote some exterior material. I actually use the let me show you. Okay, this is the assignment. Okay, these questions are in each section from 3, 4, 5, 6. I give almost at least one, at most 2 questions. Now, the additional question on R is that you use. I will ask you to use this data set. Okay, where you can see here. Okay. Where you can see here. Okay, this is the data. So you should copy and paste this in in a text file and read it as a space delineated data set, and so you can practice how to do that to turn your data into a CSV file as well. Okay, import it into Excel and turn it into CSV file and save it and use R to read it. This is I use SAS data set, so and for the data, and then you also have SAS analysis based on that data set for multiple regression. I do this for a purpose that you can compare your result with SAS and see how it goes. Okay, this is SAS results, and you see all the results are here, but then you are not using you're not using you're not using the SAS for it. You use R. Okay, yeah, and then see how it goes. All right. Yeah, basically, you should be able to get all these that our SAS has analyzed. Like this is what residual student predicted. This is part of predicted values, student ties residual without current observations. This is residual plot. Okay. There seems still be a little bit pattern. Not too bad. Okay. So you go you go home and study this. You can refer to the outcome and compare it with yours, and do as much as you can. There's no standard. Actually, this is a standard solution, but you may come up with a different result because you are using R, and they should not deviate from each other too much. Okay, all right. Okay, let's see. Any question, Paul?
No. I've got to review the matrix stuff a little bit. That's kind of beyond where I was before with linear regression, but no, I think everything's pretty much clear cut. I honestly think regression analysis is as important as like the central limit theorem because we use it all the time.
Mm-hmm.
And we're always trying to figure out if there's a relationship, and everybody yells eureka when it's linear between 2 or 3 different variables. So yeah, I think I'll struggle through it, and if I have any questions, I'll send you an email.
Okay.
No, it's pretty clear.
Okay, very good. Okay, and hope that yeah, we should be able to. I need to check the next the rest of the modules. We should have logistic regression, which is also very useful as well. And get to practice the regression application in these. And when you extend that to linear regression, that's even more useful. Okay. And so this, yeah, indeed, yeah, like what you say, yeah, I agree. Central limit theorem is one a part of the 2 hinges. Okay, in the door open people into inferential statistics from descriptive. One is central limit theorem, and regression analysis might be another.
It is. No, definitely it is.
Okay, very good. All right. Good. I better that you eat your dinner with your wife. Okay.
I'll start here now. Okay, thank you.
Okay. Awesome. All right, good. I wish you have a wonderful evening. Okay.
Thanks. You too. Bye.
Bye.